Hello, QST readers worldwide. I'm Dave Kassler, amateur radio call sign KE0OG, here with the August 2023 video supplement to the Ask Dave column in the August QST, which is this one right here. The second story has to do with measuring transmission line parameters using an antenna analyzer. What we're going to do today is just measure a couple things: cable attenuation and length. And the antenna analyzer that we're going to use is the Nano VNA. Okay, so this is a very simple setup. Here is the cable that's under test. It's times microwave, it's real times microwave, LMR 400. The connectors are times microwave that I put on myself. It's been taken out of service, meaning it's been outside for about a year. And yesterday my wife and I measured it. It's 151 feet long. It's a long piece of coax. Now here are the factory specs that come from Times Microwave, and this is a screenshot from their website. I looked up the attenuation at 6 frequencies: 7 megahertz, 21, 100, and 146. Why did I pick 100? That's not a hem band. I picked that because that is where cable is usually specified, at 10 and then again at 100. And we see here also that the velocity factor of the cable is 0.84. And that's very important for putting that into the program so it can calculate length. Here's the test setup. It's around the Nano VNA, but what is most helpful on the Nano VNA website is the Nano VNA Saver software. This thing, you plug a USB cable into this and into the computer, run this software. Very easy to do. It doesn't need installation on your PC. It will just run on your PC. You do have to specify the COM port and do a connect. Now it's USB, I know, but it acts like a COM port. So this software plus this, and then I needed 3 terminations for the end of the coax in order for these various parameters to be measured. One is a shorted. This is a SO239 that we can screw into the end of the coax, and this one is shorted. This one right here has a 50 ohm load. That's a 47 ohm resistor and a 3.3 ohm resistor to get me close to 50 ohms. Another way that you could do that using standard value resistors is to put 2 100 ohm resistors in parallel. It will do the same thing. You see they're connected from the center conductor over here to the shield. And then there's an open one where there's actually no connection at all. Okay? Now, if you put RF down a cable that is shorted or open, either way, it will bounce back. And that's what we're going to use to measure cable loss. If you put a 50 ohm load on it, then you've got a good match, and the cable loss figure is erroneous because most of the energy that went into the cable is not reflected, but rather is absorbed in the load. So I used the Nano VNA software to try shorted 50 ohm and open loads for those frequencies that I mentioned earlier, 721, 100, 146. These are the specified attenuation figures here. Now, this is what a corner of that software looks like. You see the start and stop points for the sweep, and you can put markers in there and so on. This happens to be 7 megahertz for a 50 ohm load. And even with this much coax, of course, the coax loss does mask the SWR, but we have an absolutely excellent SWR, 1.051 to 1. That's excellent. That is almost 1 to 1. Now, if we go to the next one, things get a little more interesting. Here is where we put an open load on the end of the cable. The VISWAR goes up to 12.9, Okay, you can actually convert viswar and return loss into each other. The return loss here means 1.3 decibels of the signal are lost. You send it out, it bounces back off the open end and comes back, and it will be 1.34 dB less. That's round trip, okay? Now, similarly, when we do a shorted load, we've got a very similar return loss, minus 1.22, meaning that you lose that much signal, and since there is no load, it's shorted, all of the signal is either returned, either creates heat loss or is returned back to the beginning, a viswar of 14.2. Okay, let's do a little figuring here. Remember that the return loss is twice the cable attenuation because you're going two ways. You're going out to the end of the cable, being reflected, and coming back. So if we take the two estimates of return loss at 7 megahertz, 1.34 dB and 1.22 dB, they average to 1.28 dB. Now divide by 2 to get the cable loss in dB is 0.64. That's the loss for 151 feet of cable. So if we correct for the length of the cable, 0.66 to get from 150 down to 100, we get a cable loss of 0.42 dB. Now the specification is 0.3 dB for 100 feet. But you will notice if you take into account the coax connectors, which do have a little loss in them, there's one at each end, you're going to have maybe 0.06 dB. Usually people take about 0.1 dB, sometimes more. And then you will find that if you compare the spec and the cable, which now has connectors on it, specification is without connectors, it's actually very close. So let us take a look at the cable loss at 721, 100, and 146. Here is the open value, the shorted value. We average the two. Okay, divide by 2 to get the one way. Convert it down to 100 feet. Okay, so this is the loss per 100 feet right here. We compare that to the factory data, the spec, and we get a small delta here. 0.1, 0.1, 0.2, or actually that's closer to 0.3, 0.2. And we get back to those connectors again. Different people attribute different loss to connectors. Now, we also can measure cable length. To do this, we have to tell the software that the velocity factor is 0.84 because it assumes a velocity factor of 0.66, which is kind of old-fashioned. We don't use much RG8 coax anymore. So the velocity factor is given by the factory as 0.84. In other locations in the factory documentation, it's given as 0.85. Nominal difference, very little difference. So if we go to 7 megahertz, now I only have the open here because when I did the closed, I had the original velocity factor in there of 0.66, but the open are all correct. So this gives you, according to the measurement, this is meters, this is now feet, 153, 160, 144, 141. The measured is 151 feet. So this is the delta in feet, and this is the percent that were wrong. Notice in this case, at 7 megahertz, it's less than 2% wrong. But it gets up to a little higher, 6% and 4% wrong. Now, what does this mean? Well, it can mean several things. First of all, the velocity factor may not be constant across all frequencies. It may vary slightly. Another thing, of course, is that the nano-VNA may not measure it exactly right. But we're within 10%, which for most electrical measurements is actually pretty good. Okay, now I want to make a comment on the 144 megahertz band, the 2 meter band. This is the entire display showing the SWR across the 2-meter band with a cable that is open at the end. Okay, it's open. Now, this shows that in some parts of the band, the SWR goes below 3. That's with an open cable. Can you match 3 to 1 on 2 meters? Yes, actually you can. You can have it look like 1 to 1 to the transmitter. Okay? But there's no antenna at the end. So all of the power is lost in the cable. And if you're putting out 100 watts, you're heating that cable by 100 watts. So this is something you need to really watch out for at VHF. The cable attenuation at the higher frequencies can mask SWR problems at the antenna. The SWR, obviously, at an open coax is infinity. But by the time you attenuate things, do the math, you get down under 3 to 1 in certain parts of the band. Moral of the story? The moral of the story is simple. Be sure to make sure that your antenna is properly matched so that you don't lose all your power, both going up and coming back for on receive, is not lost. Okay, in conclusion, I think we can say that even with amateur level test equipment, we can get pretty close to estimating cable loss and cable length. No piece of coax will ever exactly match the published parameters, so it usually will come pretty close. Now, it's not just cable loss, but also connector loss that contributes to measured loss. We showed connector loss of anywhere between 0.1 and 0.3 dB. Some people say that connectors are as high as 1 dB, but we certainly didn't measure that here. And at VHF and UHF, cable losses can mask high SWR. So you need to measure your antenna a little closer to the antenna. And anyway, a 151-foot run, even of LMR 400, is a pretty long cable for VHF. I would suggest really cutting that down to 25 or almost 50 feet. And on a personal note, now that I've learned to use it, the Nano VNA is pretty cool, particularly with the Nano VNA Saver software. And it's that web address right there, which takes you to the Nano VNA organization. This is, quote, official, unquote, software from the Nano VNA group. Remember that what the Nano VNA people do is open source. So there are a lot of people, mostly Chinese, who are building these things. There is one authorized dealer in the United States for Nano VNA hardware, and that is randl.com. It's RANDL.com. Romeo Alpha November Delta Lima.com. And if you buy from them, you get the ones that the Nano VNA organization says are good. You can actually buy them from dozens of sources. I originally, not knowing that, bought mine from, are you ready for this, Walmart. So there you have it. We have shown that you can use an antenna analyzer in many different ways, not just to measure the SWR, which we can certainly do, but also take a look at things like cable length, distance to fault. You can look at the impedance of the cable. If you measure the cable, you can compute the reflection coefficient. If you know the reflection coefficient, you can calculate length. And of course, our favorite, return loss, which is round trip loss for a signal, which is half of the cable specified attenuation loss. So I hope you enjoyed that. And there you have it. And until we next meet, next month for the September monthly video, 73.